Hello, this is part 5 of a video playlist about the preparation of alkenes. This video is about the preparation of olefins from other olefins by substitution of vinylic hydrogen. This includes alkene oligomerizations, Heck reactions, Friedel-Crafts acylations, and some other types of transformation. A number of different strategies have been reported to alkylate or arylate alkenes. Olefins can be alkylated by carbocations, like the Friedel-Crafts alkylation of arenes. Mixtures of olefinic isomers or other products may result, however. Another strategy is the Heck reaction. Electron-deficient alkenes react with certain late transition metal-derived organometallics to yield substituted alkenes and a metal hydride. Most reported examples involve organopalladium and nickel compounds. Palladium and nickel only form weak bonds to oxygen, and the initial intermediate still contains a carbon-metal bond. Elimination of the metal hydride yields an alkene. During this reaction, the metal is reduced by 2 electrons. Unlike the Heck reaction, Michael additions of polar organometallics yield saturated enolates with a metal bound to oxygen. Upon hydrolysis, saturated alkanes are obtained, not olefins. No reduction of the metal occurs. Organolithium and organosodium compounds are too hard and will often undergo 1,2 addition to the carbonyl group, but let's just assume that R' in this sketch is sufficiently bulky to prevent 1,2 addition. The extent of 1,4 addition can also be enhanced by adding catalytic amounts of copper, which is softer than alkali cations. In other words, when an organometallic reagent adds to an enone, the selectivity will change from 1,2 addition to 1,4 addition to Heck reaction as we go from hard organometallics to polarizable organometallics of noble metals. Most alkenes can also be dimerized or converted into oligomers or polymers. Oligomerization can be promoted by acids, bases, or by radicals. Electron-deficient alkenes can also be dimerized to alkanes by electrochemical reduction, as sketched here. This reaction is used for the industrial production of adiponitrile and adipic acid esters. Alternatively, electron-deficient olefins can be dimerized catalytically to unsaturated adipates. These reactions are initiated by addition of a transition metal hydride to the alkene. Isomerization of the product to a thermodynamically more stable 5-membered chelate, followed by CC bond formation and metal hydride elimination, yields the observed tail-tail dimers. Let's check some specific examples. With catalytic palladium, a tail-to-tail dimer was formed from methyl acrylate by the mechanism discussed above. The dimerization was conducted without any solvent, and an uncontrolled polymerization was therefore a potential risk. To prevent this, the acrylate was stabilized with 4-methoxyphenol. Here, a similar tail-to-tail dimerization was catalyzed with 10% of a ruthenium complex. Along with the dimers, 13% of trimeric products were also formed. This here is a rare example of transition metal-free tail-to-tail dimerization of an electron-deficient alkene. The catalyst was a heterocyclic stabilized carbene. This catalyst acted by converting metacrylonitrile into a nucleophilic ketene aminal, which then added to another molecule of nitrile. Elimination of the catalyst generated the alkene dimer. Again, this reaction was run at high concentration, what generally favors oligomerizations. When acrylates are treated with strong nucleophiles, for instance phosphines or DAPCO, a head-to-tail dimerization can occur. Here, methyl acrylate was dimerized this way with the aid of a particularly nucleophilic phosphorus amide. Also non-activated alkenes can be dimerized, but not as well as acrylates. Here, 1-octene was dimerized to a mixture of olefins with a chromium catalyst and a Lewis acid, but the conversion was only low. Synthetically more interesting than dimerizations are alkylations, arylations, and acylations of alkenes with different reactants. These reactions can be challenging, however. In this example, styrene was alkylated with 1-bromodecane. An excess of styrene together with titanosin dichloride as catalyst and a slight excess of butyl magnesium chloride were required. A fair yield of the target styrene resulted, along with some byproducts. The alkylation probably proceeded by intermediate formation of alkyl radicals. The rate and efficiency of radical additions to olefins can be enhanced by choosing reacting partners of diverging electron densities. For instance, electron-rich alkenes react best with radicals substituted with electron-withdrawing groups, as in this example, while electron-rich radicals add best to electron-deficient alkenes. Here, an electron-deficient radical was generated from methyl 2-bromopropionate and catalytic iron 2. In this example, a carbon-centered radical was generated by copper-catalyzed oxidation of a malonic ester. A mixture of two isomeric alkenes was obtained in high yield, despite the low concentration of reactants. Enones are another type of electrophile capable of alkylating electron-rich alkenes. Here, 10% of hafnium triflate was used as Lewis acid to further enhance the electrophilicity of the enone. Alpha-phenylstyrene gave a high yield of alkylated alkene, but with unsubstituted styrene the yield was much lower. Interestingly, with iron trichloride as Lewis acid, a hetero-Diels-Alder reaction occurred, instead of a simple alkylation. Such outcomes cannot be predicted and must be established by experimentation. Conjugated dienes are particularly nucleophilic and, with the exception of the Diels-Alder reaction, tend to yield product mixtures. In this example, methyl acrylate was allylated with a 1,3-diene and a cobalt catalyst. With alkynes, it is possible to vinylate alkenes, as shown here. In this case, the reaction was brought about with 2% of an iridium complex in methanol. I'll show you now some palladium-catalyzed Heck-type transformations of alkenes. As discussed above, unlike in the Michael addition, here a reduced palladium hydride is formed as byproduct. The required organopalladium or nickel intermediates can be generated from a number of different electrophiles. Most reported examples start with an aryl halide, but many other electrophiles can be used. Reaction of the electrophile with palladium 0 gives the required organopalladium compound. If the reaction is conducted in the presence of a base, palladium 0 will be regenerated from the palladium hydride, and catalytic amounts of the expensive palladium will be sufficient for a complete conversion of starting materials. Another strategy to generate organopalladium intermediates is oxidative palladation. Certain organic compounds, in particular those capable of forming 5-membered chelates, will undergo insertion of palladium 2 into a CH bond. In order to be catalytic in palladium, stoichiometric amounts of an oxidant must be added to regenerate palladium 2 from palladium 0. The Wacker process for the oxidation of ethylene to acetaldehyde also belongs to this class of reactions. This here is a typical example of Heck reaction. Palladium 0 was formed from palladium acetate by reduction, probably by DMF. No ligands were used because aryl iodides are very reactive and will even react with precipitated palladium black to aryl palladium iodides. Sodium acetate was required as base to remove hydrogen iodide from the palladium hydride and regenerate palladium 0. With aryl iodides, it is even possible to catalyze Heck reactions with copper, as in this example. Aryl bromides, however, gave much lower yields. In this example, an aryl bromide was coupled with a styrene with the aid of only 0.05% of palladium acetate, again without any phosphine ligand. Despite the high reaction temperature, no deformylation occurred. Benzaldehydes sometimes lose carbon monoxide upon heating with palladium or rhodium complexes, but this did not happen here. This is another example of optimized Heck reaction. The aryl bromide reacted selectively, while a less reactive aryl chloride remained unchanged, despite the use of a bulky phosphine ligand. Instead of aryl halides, vinyl halides can also be used as electrophiles. Here, a geminal vinylic dibromide underwent intramolecular Heck reaction only once to yield a conjugated diene. Aryl chlorides are quite unreactive and often require bulky, electron-rich phosphines to react at all with palladium. Here, 4-chloronitrobenzene was coupled with styrene with the aid of such a bulky catalyst. Under more forcing conditions, it's even possible to displace nitro groups, but this did not happen here. I'll show you an example of nitro group substitution in a minute. Arene diazonium salts are strong oxidants and electrophiles, and their use in Heck reactions often requires extensive optimization. Here, an unactivated vinyl group was arylated in high yield with only a slight excess of a diazonium tetrafluoroborate. Iminium salts are common electrophiles in organic synthesis. Normally, these are not electrophilic enough to alkylate styrenes or unactivated olefins. With palladium 0, however, alpha-palladated amines can be formed, which then undergo a Heck-type addition to simple alkenes. In this example, this technique was used to aminomethylate a substituted styrene. Activated carboxyl groups can be better leaving groups than chloride in Heck reactions. Here, 4-chlorobenzoic acid was converted into a mixed pivalic anhydride and then coupled with dimethylacrylamide. A high yield of the expected cinnamamide resulted. As mentioned, even nitroarenes can act as electrophile in Heck reactions. Here, both a bulky phosphine and a high reaction temperature were required, and the yield of arylated alkenes wasn't high, but this should be kept in mind as one potential side reaction. Also, aliphatic halides and other electrophiles can be suitable for Heck reactions. Here, cyclopentene oxide was coupled with coumarine, and a mixture of 2 diastereomeric hydroxyethylarenes resulted. Because Heck reactions require catalytic palladium 0 and sometimes phosphine ligands, strong oxidants can poison the catalyst and lower its efficiency. During the optimization of this example, it was found that old bottles of NMP contained a peroxide which had a detrimental effect on the yield. Better results were obtained with peroxide-free NMP. Oxidative Heck reactions do not require an organic electrophile. Some oxidized metals react directly with arenes, as is sketched here, to yield metallated arenes. The regioselectivity of such metallations can be controlled with a chelating substituent at the arene. Unlike the normal Heck reaction, here the catalyst must be regenerated not by a base but by oxidation. To prevent precipitation of palladium 0, ligands are also sometimes required. Phosphines are generally too sensitive to oxidants, and carboxylates or pyridines are better suited as ligands for these oxidative Heck reactions. In this example, methylcrotonate was phenylated with a huge excess of benzene and 1 equivalent of benzoyl terzbutyl peroxide. The solvent was acetic acid, and dichloropyridine turned out to be a suitable ligand. Interestingly, mostly one stereoisomer was obtained. Unlike in the previous example, here only 1 equivalent of arene was vinylated with a slight excess of ethyl acrylate. The regioselectivity of arene palladation was established by chelation with the carboxylate. A small amount of N-acetyl isoleucine was used as ligand, and the reaction conditions were somewhat alkaline. In this example, no chelate was formed, but the oxidative olefination still occurred with high regioselectivity. Unfortunately, 10% of palladium acetate was required, what is way too much for any practical application. But as shown in the previous examples, such reactions can also succeed with less catalyst. Instead of electron-rich arenes, also enol ethers can be alkenylated by oxidative Heck reaction. Here, a protected glycal cleanly reacted with an excess of ethyl acrylate. The stoichiometric oxidant was copper triflate. Alkenes can be acylated by acyl chlorides or other reactive acylating reagents, just like arenes. Under the standard Friedel-Crafts conditions, that is, in the presence of strong Lewis acids, mostly allyl ketones are obtained. The yields are low because the intermediate cation tends to react with the starting alkene, but this may be suppressed by lowering the concentration of reactants. Allyl ketones are thermodynamically less stable than conjugated enones and tend to isomerize to the latter. This isomerization can be sped up by weak bases, for instance pyridine. The intermediate carbocations or the conjugated enones readily react with nucleophiles, and chloroethyl ketones can result as byproducts. This addition of nucleophiles tends, however, to be reversible and may be suppressed by weak bases. This here is a typical example of the Friedel-Crafts acylation of an alkene. Acetylation of one hexene with acetyl chloride yielded a mixture of 2 allyl ketones and a chloroethyl ketone, but no conjugated enone. Higher yields of enones can be achieved by combining a weak base with a Lewis acid. Here, 50% of the expected enone resulted, together with 13% of olefinic isomers. Without dibromopyridine, mostly the allyl ketone would have been obtained. Particularly reactive are alkenes that yield a tertiary carbocation upon acylation. 2-ethyl-1-butene, for instance, was acylated in high yield by treatment with acetic anhydride and zinc chloride at room temperature. These mild conditions were not sufficient for acylating less reactive alkenes, as shown in the second equation. Like acyl chlorides and anhydrides, also nitrilium cations can be electrophilic enough to acylate alkenes directly. Here, such a nitrilium salt was generated from an amide and triflic anhydride. No additional Lewis acid was required for the acylation of styrene. Hydrolysis yielded the final enone in high yield. A completely different acylation strategy is the addition of acyl radicals to alkenes. Acyl radicals are electron-rich and react well with electron-deficient alkenes, as in this example. Here, the acyl radical was generated by oxidizing a benzaldehyde with tertsbutyl hydroperoxide. Alkenes can also be alkoxycarbonylated or carboxylated, for instance with Lewis acids and carbon dioxide. In this example, a combination of carbon monoxide, the oxidants DDQ and benzoquinone, and 10% of palladium acetate was used to bring about the methoxycarbonylation of allyl benzene. Well, I've covered in this video a rather diverse group of reactions, which however can all be used to replace vinylic hydrogen with carbon. A lot of research is being done in this area, and this is only a small selection of further references. You can also find these in the description of this video. Under the Community tab, there's a PDF version of this presentation for subscribers. The next video of this playlist is about the preparation of olefins from alkynes. Alkynes are readily available by dehydrohalogenation or from other alkynes, and are therefore interesting starting materials. See you!